My name is Harrysone Atieli from Sub-Saharan ICEMR. Now, I'd like to present the impact of environmental modifications on malaria vector ecology and transmission. Now, first, I'd like us to look at the challenges that limit malaria control effectiveness. Now, as we are aware, first-line vector control tools such as long-lasting insecticide nets and indoor residual spraying are mainly targeting indoor vectors. Now, as a result of this pressure, now vectors have now devised a mechanism to avoid this. So we are seeing a lot of outdoor biting, shifting biting time, feeding on multiple hosts, and resting outdoors. Now, outdoor transmission and insecticide resistance we know are very important in malaria transmission. And this can be aggravated by environmental changes and climate change. Now, when we look at some of these activities within our study areas, such as mixed crop irrigations, these are activities that are modifying environment that may be conducive for vector activities. Now, like here, habitat diversity, we can see is a cause of these irrigation activities that have now cropped up in these areas of irrigation. Now, when we compare this between two areas of Ethiopia and Kenya, we can see both sides have irrigation activities. Now, our team went out to ask two questions. How do environmental changes modify vector ecology and transmission dynamics across diverse epidemiologic settings? And number two, are there alternative surveillance and control methods to reduce outdoor transmission? So look at this data. Now, from our data, we went out to look at what about habitat abundance when we compare these two ecosystems. Now, one being irrigated and non-irrigated. Now, when we surveyed these areas, just to check about habitat abundance, we realized that throughout the seasons, this is both during the dry and the rain season, the irrigated zones tend to have more habitats than non-irrigated areas throughout the two seasons. Now, looking at habitat stability, these habitats that maintain the aquatic status either throughout the dry or rain season. Now, irrigated areas were better in maintaining the aquatic status in these habitats, and with over 72% of the habitats maintaining the aquatic status during both the rain and the dry season. Now, these habitats were also important that we check if they are for sure productive. And productivity in this sense, I mean that they were able to sustain the larval to the people to the other stages of mosquitoes. And equally, the areas within the irrigated zones were very productive compared to those in non-irrigated zones. So it was interesting that what about looking at what is happening indoors? Because we're expecting that the indoor mosquitoes densities will also be affected if these areas for sure tend to have higher mosquito productivity compared to each other. And from erythrum spray collections, we realized that the houses within irrigated zones will always have high densities of mosquitoes per house per night throughout the 3 to 4 years that we did our survey. Now, that particular surveys were done monthly. Now, we went further to look at the impact of irrigation on malaria transmission in density. And when focusing on EIR, both indoors and outdoors using CDC light trap, we realized that in areas within the irrigated area, we are having very high infection bites per person per year compared to non-irrigated areas. And this was very significant. Now, even when we collected mosquitoes using erythrum spray collection indoors, the same was still reflected. Now, comparing this data on EIR in Ethiopia, we realized equally still malaria transmission density was higher in irrigated areas than non-irrigated areas. Now, our team went further to look at what about surveillance tools. And looking at the conventional vector surveillance tools, we know that they have their limitations. When you look at human landing catches, CDC light trap method, they have challenges such as you need CO2 for you to implement these tools in the field. They are labor intensive. There is exposure risk to the people doing the collections, and equally, there is need for electricity or power source in the field. Now, so our team wanted to see if they can come up with alternative outdoor vector surveillance tools. And three of these are here on display. The first one is sticky clay pot. Second one is human audit tube CDC light trap. And the third one is human baited double net CDC light trap. And now, what are some of the advantages of these particular alternative outdoor vector surveillance tools that our team came up with? Is that these ones are locally available, they are low cost, most of them, and no need for supply of CO2, and also they are human exposure free. Like if you look at the double net on your far right, which is simulating human landing catches, it's human exposure free because the person is deep inside the second net in there. Now, looking at their performance in comparison to the conventional CDC light trap, we realized that the sticky clay pot, like in Kenya, was comparably well doing compared to the CDC light trap. And when we looked at the studies we did in Ethiopia, the human baited double net and the human order baited CDC light trap were doing even better than conventional CDC light trap. So it means some of these can be considered as vector surveillance tools. Now, we went further to look at outdoor resting mosquito surveillance because of the changes I mentioned above, that some of these vectors are now changing their biting behavior and also resting behavior. And the main question was that, can such information be valuable to develop targeted outdoor intervention tools if for sure we can know their outdoor resting and sugar feeding behaviors? And out of the many resting sites that we found, I'm displaying here some of the top 7 resting sites that we found. And in comparison to the first occupied house, these other 6 outdoor resting sites had lots of mosquitoes based on our collections. Now, let us look at alternative outdoor vector control tools. Now that for sure we are seeing there are so many activities of mosquitoes out there. Now, this picture is displaying the Kenya Malaria Army initiated by the ALMA. And here is the Kenyan president initiating larviciding activities within the Kenyan coast for larval control. And look at this. This is the amount of money that is being pumped into this particular project. It means there's a lot of attention for biological methods to be used in vector control. Now, conventionally, we know of this biological larvicide, and this particular formulation has been known conventionally to be effective for between 7 to 10 years. But now, there's a long-lasting formulation which is known to be effective for several months. So our team went out, both in microcosm and also in the field, to test the efficacy of this particular larviciding. And at the end of the day, we looked at the indoor and outdoor densities of mosquitoes within the areas of treatment and control. And we found that the areas with this long-lasting larviciding control, treatment, had lower densities compared to areas that were controlled without the treatment. So this particular long-lasting larvicide is equally important in vector control. Now, looking at the spatial repellents, these are commercially available spatial repellents, which are alternative vector control. Now, as a tool, we know that pyrethroid resistance is widespread in Africa, and globally, mosquito repellents market is so high. They're spending lots of billions, like in 2022 projection, we are talking about $5 billion. Now, evidence on the efficacy of spatial repellents comes mainly from pyrethroid susceptible mosquitoes. But now, what about the same commercial spatial repellents on resistant mosquitoes? Because we know insecticide resistance is a major impediment in malaria control. So we went out to do investigation in malaria sphere through tube bioassays to see if this can have an effect on resistant mosquitoes by looking at both repellent release point, looking at mosquito release point and attractant release points in this malaria sphere. Now, at the end of the day, we tested several commercial spatial repellents, and some of them are displayed here. And we also described their mode of action and active ingredients. Now, what about our results? Now, just picking one example out of these many spatial repellents, we realized that these spatial repellents are good on both susceptible and resistant mosquitoes, where they were deterrent factor when you put them in a treatment house compared to the house that has no treatment. So it's important that we look at multiple of them. So when we looked at now all the array of these commercially available spatial repellents, we realized that the trend was similar, where they had with these particular spatial repellents had lesser mosquitoes getting inside the houses compared to the houses which had no repellent. And this was both for susceptible and resistant mosquitoes. So they are working well for both resistant and susceptible mosquitoes. Now, what happens at the end of the day with all this information and with all these tools? How do we enhance vector surveillance and control tools? Is by field validation across epidemiologic settings, optimal combination of existing and new control tools, and also looking at the epidemiological impact to assess which ones are better when either used in combination or in singular. Thank you so much.